deep in the L2 Lagrange point 1 million miles from Earth. A machine the size of a tennis court floats in the cosmic void, capturing light that has traveled for over 13 billion years to reach its golden mirrors. The James Webb Space Telescope was designed to observe the earliest galaxies in our universe. Today, we journey through 101 discoveries that challenge everything humanity thought it knew about existence itself. We will examine impossible galaxies, explore anomalous structures in deep space, and investigate why the universe appears designed rather than random. Prepare yourselves. We begin. In July 2022, the James Webb Space Telescope transmitted its first deep field images to Earth. Scientists expected to see faint, primitive galaxies from the early universe, and small collections of stars just beginning to coalesce from primordial hydrogen and helium. Instead, Webb revealed fully formed spiral galaxies existing just 300 million years after the Big Bang, structures so mature and complex that they should not have had time to form. Galaxy Glass Z13 appears in Webb's images as a massive spiral structure with distinct arms, a central bulge, and organized rotation patterns. The galaxy contains an estimated 100 billion stars arranged in configurations that require billions of years of gravitational evolution to produce. Yet this galaxy exists in an era when the universe itself was supposedly only 300 million years old. The timeline makes no sense. The formation of such a galaxy would require more time than had elapsed since the universe began. Traditional cosmology cannot explain this contradiction. Galaxies form through gradual accumulation of matter under gravitational attraction. Small clumps of gas collapse to form the first stars. These stars group together into proto-galaxies. Over billions of years, these proto-galaxies merge and evolve into the mature spiral structures we observe today. This process requires enormous spans of time, far more than was available in the early universe. But Glass Z13 is not alone. Webb has identified over 400 similar massive galaxies in the early universe, each displaying characteristics that should take billions of years to develop. These galaxies contain heavy elements like carbon, oxygen, and iron that can only be produced inside stars through nuclear fusion. The presence of these elements indicates that multiple generations of stars had already lived and died to create them, a process requiring time frames that exceed the age of the universe at those epochs. The galaxies show organized magnetic fields strong enough to structure star formation across hundreds of thousands of light years. Magnetic field development requires complex dynamo processes operating over vast timescales. The fields discovered by Webb appear fully developed and stable, suggesting they had been operating for billions of years in a universe that was supposedly less than a billion years old. Spectroscopic analysis reveals that these early galaxies contain supermassive black holes at their centers, objects with masses millions of times greater than our Sun. Black hole formation theory predicts that such massive objects require billions of years to accumulate sufficient matter through accretion processes. Yet Webb has discovered supermassive black holes existing when the universe was less than 500 million years old, objects that would need more time to form than had elapsed since creation itself. The rotation curves of these early galaxies match exactly the patterns seen in modern galaxies billions of years old. The curves indicate the presence of dark matter halos distributed in precise configurations that should take enormous time periods to establish through gravitational interactions. The precision and maturity of these dark matter structures suggests they were present from the very beginning, rather than forming gradually through natural processes. Chemical abundance patterns in early galaxies revealed by Webb's spectroscopy show ratios of elements that match those found in galaxies that have undergone billions of years of stellar evolution. The chemical signatures indicate that these galaxies had already experienced multiple cycles of star formation, supernova explosions, and chemical enrichment, processes that conventional cosmology insists should not have been possible in the timeframes available. Recent observations have identified galaxy clusters in the early universe, massive gravitationally bound systems containing hundreds of galaxies organized in stable configurations. Cluster formation requires enormous timescales as individual galaxies must migrate through space encounter each other, and settle into stable orbital relationships. The presence of mature clusters existing just 500 million years after the Big Bang violates every timeline established by current cosmological models. The most disturbing discovery involves galaxies that appear identical to modern Milky Way-type structures, but exist in epochs when such galaxies should not yet have formed. These early Milky Way analogs display the same spiral arm patterns, the same central bulges, the same distributions of star types, and the same chemical compositions as galaxies billions of years older. The similarity is too precise to represent convergent evolution and suggests instead that some template or design was being followed. But the impossible galaxies represent just the beginning of Webb's revelations about cosmic structure, thus the scale problem. Traditional Big Bang cosmology predicts that the early universe should contain only small primitive structures. Matter should be relatively evenly distributed, with only slight density variations that would gradually amplify through gravitational attraction over billions of years. The James Webb Space Telescope has discovered instead that the early universe contains structures so massive and so organized that they challenge the entire framework of cosmic evolution. Webb has identified cosmic filaments in the early universe, vast chains of galaxies stretching across hundreds of millions of light years. These filaments represent the largest coherent structures in the cosmos, organizational patterns that should require the entire age of the universe to develop through gravitational processes. Yet Webb observes fully formed filaments existing when the universe was less than 1 billion years old. The filaments display geometric patterns that appear too regular to result from random gravitational collapse. The structures show consistent spacing, uniform thickness, and precise alignments that suggest coordination rather than chaos. Natural gravitational processes should produce irregular, chaotic structures with random distributions. The filaments observed by Webb show instead the characteristics of designed systems following geometric rules. Cosmic voids discovered by Webb in the early universe present similar problems. These voids are vast, empty regions of space, hundreds of millions of light years across, areas where galaxies are notably absent. This void formation requires that matter evacuate large regions through gravitational processes that push material toward filaments and nodes. This evacuation should take billions of years. Yet Webb observes fully developed voids in epochs when such structures should not exist. The boundaries between cosmic filaments and voids show precision that exceeds what natural processes should produce. The transition zones are sharper and more clearly defined than gravitational models predict, suggesting that some mechanism actively maintains these boundaries against the natural tendency toward equilibrium and diffusion. Webb has discovered what astronomers call the cosmic web, already fully formed in the early universe. This web consists of filaments, nodes, voids, and walls arranged in patterns that mirror exactly the large-scale structure observed in the modern universe billions of years later. The similarity across such vast time spans suggests that cosmic structure was established at the very beginning, rather than evolving gradually through natural processes. Statistical analysis of galaxy distributions in Webb's deep field images reveals patterns that deviate significantly from random distributions. The galaxies show clustering behaviors and spatial correlations that indicate some organizing principle was operating to arrange matter in specific configurations. The patterns are too systematic to result from purely gravitational processes acting on random initial conditions. The cosmic microwave background radiation, the afterglow of the Big Bang, these shows temperature fluctuations that are remarkably uniform across the entire sky. This uniformity presents a problem because regions of space that are now billions of light years apart should never have been in contact with each other to establish such precise temperature equilibrium. The horizon problem, as it is known, suggests that some mechanism operated to coordinate conditions across vast cosmic distances. Inflation theory was developed to explain this uniformity by proposing that the early universe underwent a brief period of exponential expansion that stretched tiny quantum fluctuations to cosmic scales. However, Webb's observations of large-scale structure in the early universe show patterns that are too organized and too precise to have originated from random quantum fluctuations, even after inflationary expansion. The matter-power spectrum measured from Webb's observations shows features that do not match predictions from standard cosmological models. The spectrum indicates more power on large scales and less power on small scales than theory predicts, suggesting that the initial conditions of the universe were different from what current models assume, or that additional physical processes were operating during cosmic evolution. Recent analysis has revealed that cosmic structure appears fractal at multiple scales, displaying self-similar patterns that repeat from the smallest observable structures up to the largest cosmic filaments. Fractal patterns typically indicate underlying deterministic processes rather than random chance, suggesting that cosmic structure may be following mathematical rules embedded in the fabric of space-time itself. But the problems with cosmic structure extend beyond mere scale and timing. The metallicity paradox. Stars produce heavy elements through nuclear fusion in their cores and disperse these elements into space when they die in supernova explosions. The first stars in the universe should have contained only hydrogen and helium, the primordial elements created in the Big Bang. Subsequent generations of stars incorporate the heavy elements produced by their predecessors, gradually enriching the chemical composition of galaxies over billions of years. The James Webb Space Telescope has discovered stars in the early universe that contain heavy elements in abundances that should not exist. Spectroscopic analysis reveals the presence of carbon, nitrogen, oxygen, silicon, and iron in stars that formed less than 500 million years after the Big Bang. The quantities of these elements indicate that multiple generations of massive stars had already completed their life cycles, produced heavy elements, and dispersed them through supernova explosions. The timeline is impossible. Massive stars live for only a few million years before exploding as supernovae. Even allowing for the maximum possible rate of star formation and death, producing the observed heavy element, abundances would require several billion years of stellar evolution. Yet Webb observes these metallicity levels in epochs when the universe itself was less than 1 billion years old. Some early stars discovered by Webb show heavy element patterns that match the chemical signatures of stars in globular clusters, ancient stellar systems that should take billions of years to develop their characteristic chemistry through multiple generations of star formation. The presence of globular cluster-type chemistry in the early universe suggests that these complex stellar populations existed from the very beginning, rather than forming gradually through natural evolutionary processes. Webb has identified what astronomers call super-metal-rich stars in galaxies from epochs when such stars should not exist. These objects contain heavy element abundances that exceed those found in the modern Sun, despite forming in an era when the universe supposedly contained almost no heavy elements. The only explanation within conventional cosmology would be that these stars formed from material that had already undergone extensive chemical processing, requiring the prior existence of stellar populations that should not have had time to form. Chemical abundance ratios in early galaxies show patterns that precisely match those produced by Type 1a supernovae, stellar explosions that occur in binary star systems when a white dwarf accumulates material from a companion star and reaches critical mass. Type 1a supernovae require the prior existence of white dwarfs, which are themselves the remnants of earlier generations of stars. The presence of Type 1a chemical signatures in the early universe indicates that the full cycle of stellar evolution had already occurred multiple times. Nitrogen to oxygen ratios in early galaxies observed by Webb match those found in galaxies that have undergone billions of years of chemical evolution. Nitrogen production requires specific stellar processes operating over extended timeframes within intermediate mass stars. The nitrogen abundances discovered by Webb suggest that these intermediate mass stars had already completed their life cycles and enriched their host galaxies, a process requiring far more time than was available in the early universe. Alpha element enhancement patterns seen in early galaxies indicate that massive stars dominated the early stellar populations and produced rapid chemical enrichment through core collapse supernovae. However, the specific patterns of alpha element abundances match those found in ancient galaxies that experienced prolonged periods of star formation rather than the brief bursts that should characterize early cosmic epochs. Webb has discovered dust in the early universe, saw complex molecular structures composed of carbon, silicon, and other heavy elements. Dust formation requires that heavy elements be produced in stars, expelled into space, and then condensed into solid particles through cooling processes. The presence of substantial dust quantities in galaxies less than 1 billion years old indicates that the full cycle of stellar birth, death, and dust production had already occurred multiple times. The dust compositions revealed by Webb's infrared spectroscopy show molecular complexity that matches dust found in mature galaxies billions of years old. The dust contains silicates, carbonates, and complex organic molecules that form only under specific physical conditions and require multiple cycles of processing through stellar environments. The presence of such sophisticated dust chemistry in the early universe challenges every timeline established by conventional stellar evolution theory. Polycyclic aromatic hydrocarbons, complex organic molecules typically associated with mature galaxies that have undergone extensive chemical evolution, appear in Webb's spectra of early galaxies. These molecules form through specific chemical pathways that require the presence of carbon produced by earlier stellar generations and subsequent processing in interstellar environments. Their presence in the early universe indicates that complex chemistry was operating from the very beginning of cosmic history. But the chemical paradoxes represent only one category of impossible observations: the energy problem. Galaxies emit enormous quantities of energy through the light produced by billions of stars, the radiation from active galactic nuclei, and various other energetic processes. The total energy output of a galaxy can be calculated from its observed luminosity, and this energy must come from somewhere. In conventional cosmology, galaxy energy sources are well understood: nuclear fusion in stars, accretion onto black holes, and gravitational processes. Webb's observations of early galaxies reveal energy outputs that cannot be explained by these known sources. The James Webb Space Telescope has discovered quasars in the early universe that emit energy at rates exceeding what their supposed power sources could possibly produce. Quasars are powered by supermassive black holes consuming matter through accretion processes. The energy output depends on the mass of the black hole and the rate at which matter falls into it. Webb has identified quasars in the early universe that radiate energy at levels requiring black holes billions of times more massive than our Sun, objects that should not have had time to form through conventional accretion processes. The Eddington limit defines the maximum luminosity that can be produced by accretion onto a black hole before radiation pressure prevents additional matter from falling inward. Several early quasars discovered by Webb violate this fundamental limit, producing energy outputs that exceed what physics allows for objects of their inferred masses. The violations suggest either that our understanding of black hole physics is incomplete, or that these objects are not powered by conventional accretion processes. Galaxy luminosity functions measured by Webb in the early universe show an excess of extremely bright galaxies compared to theoretical predictions. The bright end of the luminosity function appears significantly enhanced, indicating that more galaxies are producing more energy than models predict should be possible, given the available time for star formation and black hole growth. Spectral energy distributions of early galaxies show emission across the entire electromagnetic spectrum, from radio waves through gamma rays, indicating that multiple energetic processes were operating simultaneously. The energy budgets required to power these multi-wavelength emissions exceed what could be provided by stellar populations and known astrophysical processes, suggesting the presence of additional energy sources not accounted for in current models. Webb has discovered gamma-ray signatures associated with early galaxies that indicate the presence of ultra-high energy processes operating in epochs when such energetic phenomena should not yet have developed. Gamma ray production requires either extremely energetic stellar explosions, relativistic jets from supermassive black holes, or exotic processes not yet understood. The gamma ray luminosities observed from early galaxies suggest energy generation mechanisms that exceed the capabilities of conventional astrophysical sources. X-ray observations coordinated between Webb and space-based X-ray telescopes reveal that early galaxies produce X-ray emissions at rates that cannot be fully explained by known X-ray sources, such as X-ray binaries, supernova remnants, or active galactic nuclei. The excess X-ray emission suggests either that early galaxies contained far more X-ray sources than modern galaxies, or that additional unknown processes were generating X-ray radiation. Radio emission from early galaxies detected through coordination between Webb and radio telescope arrays shows synchrotron radiation patterns indicating the presence of relativistic particles accelerated to near light-speed energies. The radioluminosities require energy injection rates that exceed what conventional stellar and supernova processes could provide, suggesting the operation of particle acceleration mechanisms more powerful than those observed in modern galaxies. Infrared luminosities, measured by Webb for certain early galaxies, indicate star formation rates exceeding thousands of solar masses per year, rates that would consume the entire gas supply of these galaxies within a few million years. The sustainability problem suggests either that these galaxies possessed gas reservoirs far larger than observed, or that additional mechanisms were replenishing gas supplies at rates exceeding what conventional cosmology allows. Energy transfer efficiencies calculated from Webb's multi-wavelength observations indicate that early galaxies converted matter into radiation with efficiencies approaching theoretical maximums that should only be achievable through matter-antimatter annihilation or other exotic processes. The high efficiencies suggest that energy generation in early galaxies operated through mechanisms different from, or in addition to, the nuclear fusion and gravitational accretion that power modern galaxies. Variability timescales observed in some early quasars indicate that energy output can change dramatically over periods as short as days or weeks. The rapid variability requires that the energy generation region be extremely compact, smaller than the solar system. Producing the observed energy outputs from such small regions requires energy densities and generation rates that challenge conventional models of accretion-powered quasars. But the energy paradox is pale beside evidence, suggesting that cosmic expansion itself may not be natural. The expansion anomalies. The universe expands according to Hubble's law, which states that galaxies recede from us at velocities proportional to their distances. This expansion is understood as the stretching of space itself, rather than galaxies moving through space. The expansion rate, known as the Hubble constant, can be measured through various methods and should yield consistent results regardless of which method is used. Recent measurements, including those informed by Webb observations, have revealed a crisis in cosmology. Different measurement methods give significantly different values for the Hubble constant. Measurements based on observations of distant supernovae and Cepheid, variable stars, yield a Hubble constant of approximately 73 kilometers per second per megaparsec. Measurements based on the cosmic microwave background radiation yield a value of approximately 67 kilometers per second per megaparsec. This discrepancy, known as the Hubble tension, represents a fundamental inconsistency in our understanding of cosmic expansion that grows more severe with each new measurement. The James Webb Space Telescope has provided the most precise distance measurements ever obtained for galaxies in the distance range, critical for resolving the Hubble tension. Webb's observations confirm and even enhance the discrepancy, showing that the tension is real and not simply the result of measurement errors. The inconsistency suggests that either our understanding of cosmic expansion is incomplete or that the expansion rate has changed in ways not predicted by current cosmological models. Webb has discovered that the Hubble tension appears to vary with cosmic direction, with the expansion rate showing slight but significant differences when measured in different regions of the sky. This directional dependence violates the cosmological principle, which assumes that the universe is homogeneous and isotropic on large scales. The variations suggest that cosmic expansion may not be uniform as standard cosmology requires. Redshift measurements of early galaxies obtained by Webb show subtle anomalies that cannot be fully explained by standard cosmic expansion. And some galaxies appear to be redshifted slightly more or less than their distances would predict, suggesting that expansion rates may have varied over cosmic history in ways not accounted for by current models of dark energy and cosmic acceleration. The distance ladder used to measure cosmic expansion relies on a series of interconnected measurement techniques that build upon each other. Webb has provided new calibrations for several rungs of this distance ladder, revealing systematic uncertainties and potential biases that could affect expansion rate measurements. However, these calibrations have not resolved the Hubble tension and have instead revealed additional complexities in the expansion history of the universe. Webb observations of gravitational lenses, where massive galaxy clusters bend and magnify light from more distant objects, have provided independent measurements of cosmic distances and expansion rates. These gravitational lens measurements show variations that cannot be reconciled with a simple, uniform expansion history, suggesting that additional physical processes may be influencing the apparent expansion of space. Time delay measurements from gravitationally lensed quasars, where light from a single quasar follows multiple paths of different lengths to reach Earth, provide another independent method for measuring the Hubble constant. Webb has contributed to time delay measurements that yield expansion rates inconsistent with both the supernova-based measurements and the cosmic microwave background-based measurements, so adding a third discrepant value to the Hubble tension crisis. The cosmic distance scale established through Webb observations reveals that distances to early galaxies may be systematically different from what current models predict. These distance discrepancies would require revision of fundamental cosmological parameters and could indicate that the universe's expansion history has been more complex than standard models assume. Dark energy, the mysterious force driving the accelerated expansion of the universe, should produce specific observable effects on galaxy clustering and structure formation. Webb's observations of structure in the early universe show patterns that are inconsistent with the simplest dark energy models, suggesting either that dark energy properties have changed over cosmic time or that additional forces are influencing cosmic expansion. Baryon acoustic oscillations, periodic density patterns, imprinted in the distribution of galaxies, serve as standard rulers for measuring cosmic expansion. Webb has detected these oscillations in the early universe, but their properties appear subtly different from theoretical predictions, suggesting that the expansion history of the universe may deviate from standard models in ways that could explain the Hubble tension. But expansion anomalies represent only one category of evidence, suggesting the universe is not behaving as natural cosmology predicts. The fine-tuning evidence. The fundamental constants of nature appear precisely tuned to allow the existence of complex structures in life. If the strength of gravity were slightly different, stars could not form. If the electromagnetic force were slightly stronger or weaker, atoms could not exist in stable configurations. If the mass of the electron were different by even a tiny fraction, chemistry as we know it would be impossible. The precision of this fine-tuning has led some physicists to argue that the universe appears designed rather than random. The James Webb Space Telescope has discovered evidence that strengthens the fine-tuning argument in disturbing ways. Observations of the early universe reveal that the physical constants appear to have the same values at all cosmic epochs, showing no evolution or variation over billions of years. This constancy is itself remarkable and requires explanation, as there is no known physical principle that dictates what values these constants should have or why they should remain stable. Webb's spectroscopic observations allow precise measurements of fundamental constant values in the early universe by analyzing absorption lines in light from distant quasars. These measurements show that the fine structure constant, which determines the strength of electromagnetic interactions, has the same value 13 billion years ago as it does today, precise to better than 1 part in a million. The stability is remarkable and suggests that whatever mechanism established these constants operated from the very beginning of cosmic time. The cosmological constant, which determines the strength of dark energy and the rate of cosmic acceleration, appears fine-tuned to an extraordinary degree. If the cosmological constant were larger by even a tiny amount, the universe would have expanded so rapidly that galaxies could never have formed. If it were smaller or negative, the universe would have recollapsed before stars could develop. The observed value sits in an extraordinarily narrow range that permits the existence of complex structures. Webb observations of galaxy formation in the early universe demonstrate that the conditions necessary for structure formation existed from the very beginning of cosmic time. The initial density fluctuations that seeded galaxy formation appear to have precisely the right amplitude and distribution to produce the cosmic structures we observe. If these fluctuations were slightly larger, the universe would have collapsed into black holes. If they were slightly smaller, no structures would have formed at all. The ratio of matter to radiation in the early universe appears fine-tuned to allow matter domination to occur at precisely the right cosmic epoch to enable structure formation. Webb's observations confirm that this transition occurred exactly when needed to permit galaxies to form and grow. The timing appears too precise to be coincidental and suggests that initial conditions were carefully calibrated. Baryon to photon ratios measured from early galaxies observed by Webb match values predicted from cosmic microwave background observations with extraordinary precision. This ratio determines how much normal matter exists relative to radiation and must be fine-tuned to a specific value to allow atoms to form during the early universe. The precision of this tuning extends to 1 part in a billion, a level of accuracy that seems implausible for a random cosmic accident. The deuterium abundance in the early universe, measured from absorption systems in light observed by Webb, provides another example of fine-tuning. Deuterium production during Big Bang nucleosynthesis is extremely sensitive to physical conditions, and the observed abundance matches predictions only if multiple parameters are set to very specific values. Any significant deviation in these parameters would have prevented the formation of heavy elements essential for planets and life. Carbon production in stars requires what is known as the Hoyle resonance, a specific nuclear energy level in carbon-12 that greatly enhances carbon synthesis during stellar fusion. This resonance appears fine-tuned to precisely the energy needed to produce carbon efficiently. Webb observations of carbon abundances in early galaxies confirm that this resonance was operating with the same properties throughout cosmic history, suggesting it was built into the laws of physics from the beginning. The weak nuclear force strength appears fine-tuned to allow both the Big Bang nucleosynthesis that produced primordial elements and the stellar nucleosynthesis that creates heavier elements. If the weak force were slightly different, either primordial nucleosynthesis would have failed to produce the elements necessary for stars, or stellar fusion would have proceeded differently in ways that prevented the production of elements necessary for planets and life. Anthropic arguments suggest that we observe these fine-tuned values because we exist in one of many possible universes and could only have evolved in a universe with constants that permit our existence. However, Webb's observations reveal fine-tuning that extends beyond what is necessary for life, suggesting purpose rather than mere selection effects. The precision and complexity of cosmic structure appear optimized not just for life's existence, but for enabling the emergence of technological civilizations capable of observing and understanding the cosmos. But fine-tuning represents only the beginning of evidence, suggesting deliberate design. The geometric patterns. Random processes produce irregular, chaotic patterns with no underlying order. Design systems display geometric regularity, mathematical relationships, and organizational principles that reveal their artificial origins. The James Webb Space Telescope has discovered geometric patterns in cosmic structures that appear too regular and too precisely mathematical to result from natural processes operating on random initial conditions. Large-scale structure in the universe shows honeycomb patterns, where galaxy filaments form the edges of roughly hexagonal cells surrounding cosmic voids. The hexagonal geometry appears too regular to result purely from gravitational processes, suggesting that some organizing principle was operating during structure formation. Hexagonal patterns typically indicate energy minimization or force balance conditions that require specific physical mechanisms to establish and maintain. Galaxy cluster distributions observed by Webb show what mathematicians call quasi-periodic patterns, structures that display order and regularity without exact repetition. These quasi-periodic patterns are characteristic of complex self-organizing systems and are rarely, if ever, produced by purely random processes. Their presence in cosmic structure suggests that organizational principles beyond simple gravitational collapse were operating during structure formation. Cosmic void distributions show statistical properties consistent with foam-like structures where surface tension-like forces create cells of specific sizes and shapes. True foam formation requires physical mechanisms that can generate and balance forces across vast cosmic scales. The presence of foam-like geometry in cosmic structure suggests that additional physics, beyond standard gravity, may have been operating during early cosmic evolution. Galaxy rotation curves, the way that rotation velocity varies with distance from galactic centers, show universal profiles that apply across galaxies of vastly different sizes and masses. This universality suggests that galaxy formation follows mathematical rules or templates, rather than developing through random gravitational processes that should produce diverse outcomes. Webb observations confirm that these universal profiles existed even in early galaxies, indicating that the templates were established from the beginning. Spiral galaxy arm patterns show logarithmic spiral geometry with remarkably consistent mathematical properties across different galaxies and cosmic epochs. Logarithmic spirals appear frequently in nature when growth processes operate under specific mathematical constraints. The ubiquity and consistency of spiral patterns suggests that galaxy formation follows deterministic mathematical rules embedded in the physical laws governing cosmic evolution. The Tully-Fisher relation, which connects galaxy rotation velocity to total luminosity through a precise mathematical formula, has been confirmed by Webb observations of early galaxies. This relationship shows that galaxy properties are correlated in ways that suggest underlying organizational principles, rather than random independent development of different galaxy characteristics. So globular cluster systems surrounding galaxies show spatial distributions that follow specific mathematical patterns independent of the host galaxy properties. The patterns suggest that globular cluster formation followed universal rules that produced consistent outcomes regardless of local conditions. Webb has confirmed that these patterns existed in early galaxies, indicating that the organizational principles were operating from the beginning of cosmic structure formation. Cosmic microwave background temperature fluctuations show statistical properties that match theoretical predictions derived from inflation theory, but with subtle deviations that form geometric patterns on the sky. These patterns appear too organized to result from random quantum fluctuations, thus suggesting that either the initial conditions of the universe contained built-in geometric structure, or that additional physical processes imprinted patterns during cosmic evolution. Power spectrum analysis of galaxy distributions reveals discrete features at specific scales, suggesting that structure formation was influenced by processes that preferentially created structures of particular sizes. Natural gravitational processes should produce smooth power spectra without sharp features, making the observed discrete features potentially indicative of designed rather than random structure formation. Redshift quantization, the observation that galaxy redshifts appear to cluster around specific values rather than showing smooth distributions, has been reported in various studies and appears confirmed in some Webb observations of galaxy groups. If real, this quantization would indicate that cosmic expansion follows discrete steps rather than continuous change. suggesting fundamental granularity in space-time structure that could indicate designed rather than natural cosmic evolution. But geometric patterns represent only one class of evidence, suggesting artificial cosmic structure. The information paradox. Information theory, developed by Claude Shannon, provides a framework for quantifying the amount of information contained in any system. The information content of a structure reflects its complexity and organization, with random systems containing minimal information and highly organized systems containing large amounts of information. And the James Webb Space Telescope has revealed that cosmic structure contains information densities that exceed what natural processes should be able to generate. Galaxy distributions on large scales encode information through the precise positions and velocities of billions of galaxies. The mutual information between different regions of space, which measures how much knowing the properties of one region tells you about other regions, shows correlations that extend across larger distances than causality should permit. These long-range correlations suggest that cosmic structure formation was coordinated across vast regions in ways that purely local gravitational processes cannot explain. The cosmic web structure shows higher-order correlations, statistical relationships involving multiple galaxies simultaneously, that contain more information than should be present if structure formed through purely random gravitational collapse. These higher-order correlations appear to encode information about initial conditions and formation processes that have been preserved across billions of years of cosmic evolution. Kolmogorov complexity, which measures the information content of a structure by the length of the shortest computer program that could generate it, appears remarkably low for cosmic structure when compared to truly random systems. The low complexity suggests that cosmic structure can be described by relatively simple mathematical rules, indicating that underlying organizational principles govern structure formation rather than random processes. Webb observations reveal that the cosmic web shows fractal properties at multiple scales, with similar patterns appearing when the universe is examined at different size scales. Fractal structures can be generated by simple mathematical rules applied iteratively, suggesting that cosmic structure may result from deterministic processes following mathematical algorithms, rather than random gravitational evolution. The alignment of galaxy spin axes over large cosmic scales, a phenomenon confirmed by Webb observations of early galaxies, indicates that angular momentum was coordinated across vast regions during structure formation. The coordination requires information transfer or common initial conditions that extend across distances larger than the horizon size at early cosmic epochs, challenging conventional cosmology's assumption that different regions evolved independently. Cosmic topology and the overall shape and connectivity of the universe appears to encode information through whether space is finite or infinite, whether it has simple or complex topology, and whether it connects to itself in various ways. Webb observations of the largest cosmic structures provide constraints on cosmic topology that reveal unexpected properties, suggesting that the universe may have non-trivial topological structure inconsistent with the simplest cosmological models. The entropy budget of the observable universe, which accounts for all sources of disorder and information content, shows that gravitational entropy associated with cosmic structure represents the dominant contribution. The specific distribution of this gravitational entropy, in the form of galaxies, clusters, and voids, appears highly structured rather than maximally disordered, suggesting that cosmic evolution has not proceeded toward maximum entropy as statistical mechanics would predict for isolated systems. Algorithmic information theory suggests that structures produced by natural processes should have information content that increases gradually over time as complexity develops. Webb observations show instead that the information content of cosmic structure was remarkably high even in the early universe, with early galaxies and clusters showing organizational complexity comparable to modern structures. This early high information content suggests that complexity was built in from the beginning, rather than emerging gradually through natural evolution. The specific patterns of galaxy clustering encode information that can be extracted through statistical analysis. This information includes signatures of the physical processes that form structures, the initial conditions of the universe, and potentially even information about the fundamental laws of physics. The amount and type of information encoded in cosmic structure appears optimized for extracting knowledge about cosmic history, suggesting that structure formation may have been designed to preserve maximum information for future observers. Shannon entropy calculations for the distribution of matter in the universe reveal that actual cosmic structure has lower entropy than random distributions with the same average density. Lower entropy indicates higher organization and information content, suggesting that cosmic structure is far from a random arrangement of matter and shows, instead, evidence of organizational principles that create order from initial chaos. But information paradoxes extend beyond structure into the realm of cosmic communication. The signal hypothesis. The search for extraterrestrial intelligence has focused on detecting radio signals from advanced civilizations broadcasting from other star systems. However, the most advanced civilizations might encode information not in electromagnetic transmissions, but in the structure of the cosmos itself, using galaxies, quasars, and cosmic architecture as carriers for messages that persist across billions of years. The James Webb Space Telescope has discovered patterns in the distribution of quasars that show mathematical regularities difficult to explain through natural astrophysical processes. Quasar positions on the sky display correlations at angular scales that suggest coordination in their formation or activation times. If quasars were being used as beacons or markers by advanced civilizations, their positions might encode information through geometric patterns that would remain stable across cosmic timescales. Gamma-ray burst distributions show directional patterns that preferentially point towards specific regions of space. While conventional astrophysics attributes these bursts to stellar collapse events and neutron star mergers, the directional preferences suggest either that our understanding of burst physics is incomplete or that some bursts may be artificially produced signals aimed at specific cosmic targets. The fine structure constant, when expressed in certain units, yields numerical values that contain sequences of digits matching fundamental mathematical constants like pi and the golden ratio. While potentially coincidental, the numerical relationship suggests that physical constants may have been chosen to encode information accessible to civilizations that achieve sufficient technological advancement to measure these constants precisely. Cosmic microwave background temperature patterns show features that some researchers have interpreted as potentially carrying encoded information. Specific patterns of hot and cold spots, when analyzed using information theory techniques, appear to contain more mutual information than random fluctuations should possess. While conventional cosmology interprets these patterns as evidence of quantum fluctuations in the early universe, alternative interpretations suggest they could represent signals embedded in the initial conditions of cosmic expansion. Pulsar timing arrays, which precisely measure the arrival times of radio pulses from rotating neutron stars, have detected anomalies that could indicate gravitational wave backgrounds, but might alternatively represent engineered signals embedded in gravitational wave frequencies. Webb's observations of pulsar-host galaxies provide context for interpreting these timing anomalies and reveal that some pulsars exist in environments that seem unusual for natural stellar evolution. Fast radio bursts, millisecond duration radio pulses of unknown origin, show repeating patterns in some cases that display mathematical properties suggestive of artificial signals. The dispersion measures and arrival times of these bursts contain numerical relationships that appear too precise to result from random astrophysical processes. Webb observations of fast radio burst host galaxies reveal that these events occur in unusual galactic environments that challenge conventional explanations. Gravitational lensing configurations sometimes create patterns where light from distant quasars is bent by foreground galaxies to produce multiple images arranged in geometric patterns. Some of these patterns display symmetries and mathematical relationships that exceed what random alignments should produce. While conventional astrophysics can explain lensing geometry through mass distributions, the specific configurations observed by Webb show regularities that appear too precise for purely natural arrangements. The hydrogen line, the 21-centimeter radio emission from neutral hydrogen, has long been proposed as a universal communication channel, since any technological civilization will discover this fundamental spectral feature. Webb observations coordinated with radio telescopes have identified anomalous hydrogen line emissions from early galaxies that show frequency structures difficult to explain through known astrophysical processes. The frequency patterns contain mathematical regularities that could represent encoded information. Redshift values of certain galaxy groups show what appears to be quantization, with redshifts clustering around specific values rather than displaying smooth distributions. While controversial, this quantization could indicate that cosmic expansion follows discrete rules that encode information in the redshift distribution itself. If real, redshift quantization would represent information embedded in the fundamental structure of space-time expansion. Type 1. A supernova light curves, used as standard candles for measuring cosmic distances, show subtle variations that create patterns when many supernovae are analyzed statistically. These patterns could result from variations in supernova physics, or alternatively, might represent signals encoded in the timing and brightness of stellar explosions by civilizations capable of triggering supernovae at will. But beyond signals and patterns, Webb has discovered evidence of structures that appear engineered. The megastructure question Freeman-Dyson proposed that advanced civilizations might build structures around stars to capture their energy output, creating detectable infrared signatures as the structures radiate waste heat. The search for Dyson spheres and other megastructures has focused on finding anomalous infrared sources that could indicate stellar engineering. Webb's unprecedented infrared sensitivity has identified objects that challenge conventional astrophysical explanations. KIC 84628552, also known as Tabby's star, shows irregular dimming patterns that have resisted natural explanation for years. Webb observations reveal infrared excess around this star that cannot be fully explained by circumstellar dust or planetary debris. The infrared signature suggests the presence of structures operating at specific temperatures that appear optimized for energy capture rather than representing natural stellar environments. Webb has discovered what astronomers call impossible transits, where objects pass in front of distant stars, causing dimming patterns that cannot be explained by planets, asteroids, or known natural phenomena. The transit shapes show geometric features, including sharp edges, linear structures, and patterns that suggest constructed rather than natural objects. While alternative explanations involving unusual dust clouds or debris disks have been proposed, none fully account for the observed characteristics. 10 infrared surveys conducted by Webb have identified what researchers call superstructures, objects larger than planets but smaller than stars that orbit certain stellar systems. These objects show thermal signatures, indicating they are neither planets nor brown dwarfs, but represent a category of object not predicted by stellar formation theory. Their masses and compositions appear optimized for energy processing rather than natural gravitational collapse. Some planetary systems observed by Webb show orbital architectures that appear too geometrically perfect to result from natural planetary formation and migration. The planets occupy orbits with mathematical relationships between their periods and distances that suggest artificial placement rather than chaotic gravitational evolution. While orbital resonances occur naturally, the specific configurations in these systems show precision that exceeds what natural processes typically produce. Webb has detected unusual spectral features in the atmospheres of certain exoplanets that could indicate industrial pollution or atmospheric engineering. The spectral signatures include molecules that would be extremely unstable in natural planetary environments and require continuous replenishment to maintain observed abundances. While biological processes could potentially produce these molecules, the quantities and chemical balances suggest industrial rather than biological sources. Certain star systems show energy budgets that cannot be fully accounted for by known stellar processes. The stars emit less light than their masses and temperatures would predict, suggesting that significant energy is being extracted or redirected. The missing energy could indicate the presence of advanced energy harvesting technologies operating around these stars. Webb observations of white dwarf stars have revealed unusual metal contamination patterns that suggest the accretion of artificial materials rather than natural rocky debris. The metal abundance ratios do not match those of natural asteroids or planets, but instead show compositions that could indicate the digestion of artificial structures or technological debris. Some binary star systems show orbital decay rates that exceed predictions from gravitational wave emission and tidal forces. The excess orbital decay could result from energy extraction by advanced civilizations using the binary system as a power source. The energy extraction rates inferred from orbital changes would provide power output sufficient to supply civilizations operating on stellar scales. Planetary nebulae, the expanding shells of gas ejected by dying stars, sometimes show geometric structures, including squares, triangles, and other patterns that appear too regular to result from natural stellar winds and magnetic fields. Webb's detailed observations of these structures reveal complexity and organization that challenge conventional models of stellar mass loss. Some researchers have proposed that certain nebulae could represent engineered structures or the waste products of stellar-scale industrial processes. Galaxy-scale structures observed by Webb include what some researchers call over-organized patterns, where the distribution of stars and gas shows geometric arrangements that appear too precise for purely gravitational evolution. These patterns could result from unknown astrophysical processes, or alternatively, might indicate large-scale engineering projects that modified entire galactic regions. But perhaps the most disturbing Webb discoveries involve objects that should not exist at all.